this two level logic minimization requires some heuristic sort of approach, just because the enumeration of the prime implicants will take too much time. There are too many of them. The general approach is actually quite simple. There would be some kind of loop. We will look at what those operations are, but there are some simple operations which hopefully might take us in the direction of an optimized function starting from some input function. So, we start with a cover and just attempt to improve it in different ways. What we will be studying as part of this strategy is what are those improvement operations. So, let us take a little more detailed look at some of those operations, first of which is an expansion. This just refers to the implicants that are given to us that we start off with, and they cover that n dimensional space where n is the number of Boolean variables in terms of which the function is composed. And these implicants occupy some sizes depending on the number of literals that is there in each of the implicants. So, if you have an implicant like that, then it occupies one vertex, this one occupies one corresponding to these two, and that implicant occupies two vertices, right. Each of them corresponds to some region in that cube. And the point of the expansion operation is to just try and increase the size of each implicant. Why do that? That reduces the number of literals, of course, when you expand the size, but remember the objective of the two level minimization is not merely to reduce the number of literals, it is to reduce the number of cubes, number of product terms. But the point is, when you expand one of those literals in that direction where it occupies now a larger space, it is possible that in the process you might cover some of the already existing implicants. If that happens, then you could delete the one that you have just covered as a result of the expansion. So, in this example, as we increase the size of this, it turned out that the new one actually now covers the existing implicant. So, we can drop that. So, the number of implicants has reduced from 3 to 2, that buys us something in this two level logic minimization. That is the process. And in terms of the implementation of this, so diagrammatically this should be clear. How to implement this is also an interesting problem we will get to later on, but logically what we are doing is we are changing one of the literals in that implicant to do not care. We are dropping one of those literals. In the process, of course, I should also verify that this is a valid expansion. Valid expansion means it is okay if it covers something in the on set, if it covers something in the do not care set, but it should not cover something in the off set. If it does, then that would be an invalid expansion. But that is all that is there as the basis of this expand operation. You pick up some variable. If this term has 3 variables, then along A, along B, each represents a direction, A, B and C, all 3 represent some direction along which you can perform the expansion. We can try out that expansion in different directions, and as long as it does not intersect any vertex in the offset, it is a valid expansion. We can continue the expansion. So, a second time, if you try to now expand that cube in this direction, thereby leading to this region there, this is an invalid expansion, because in the process you would be covering a vertex that is there in the offset. So, what this is telling us is you start with a function like that, this is an optimized version of that function as a result of this expand, just this one operation. We could also go the other way around. Reduce is the reverse, you are reducing the size of the implicant. Reduce here refers to the region that the implicant covers in that space. The way this comes about is you add a variable to that cube, of course. The smaller the size of the cube in terms of the number of variables that are there in it, number of literals that are there in it, the larger the space that it occupies in that space. So, this reduce just refers to in the n dimensional space how much space it covers, how many vertices it covers. What would be the point of the reduce? The point of expansion is that it improves, it ultimately reduces the number of product terms we have, which is a good thing. This operation does not lead to a more optimized solution. Right. Actually, by itself neither expand nor reduce actually lead to any difference in the number of cubes that are there. We are just changing the size of the cubes, but in the process of expansion later on you can drop some cube that is there and that would lead to a reduction in the number of cubes. Here too we are changing the size of an implicant, that does not increase or decrease the number of implicants we have, which is the ultimate objective of this optimization, reducing the number of implicants. But this itself does not necessarily lead to any improvement as it is, but it could be that you combine it with a subsequent expand operation that might lead to a better cover. It is just an elementary operation that by itself does not lead to a more optimized solution. In fact, it most probably is leading to a less optimized solution, because it is reducing the size. Of course, our objective in all of this logic minimization is that we should have these individual cubes to be as large as possible, not as small as possible. So, this could only be thought of as an intermediate step that may help us in a different expansion that might be better.
Sir, are you implying that in expansion step, wherever we expand a particular implicant, it should not overlap with an existing larger implicant? Is there a restriction of such sort?
No, I actually only covered the definitions so far. How it will be part of an algorithm we will look at, but I already hinted that overall algorithm may not be very complex. It is like a loop where you run these elementary operations until there is no further improvement.
It is hard to imagine why reduce can help us do a better expansion.
We will get to that. But so far let us just define the individual operations, knowing fully well that the last step in the algorithm cannot be reduced. Yeah, it does not help, obviously. The third one is called irredundant, that deletes some implicants from the cover that are established to be redundant. You could think of this as following the expand step. In the process of expansion, you might have rendered some implicants redundant because they got covered by the expansion process. Then we can delete that. The process of identifying that and removing that is what is included in the irredundant step. What do you do as a result of this? You need to check that when you drop one of those implicants, the cover is still valid, which is in our example here we chose to drop this implicant. Okay. In the remaining implicants after the dropping of that particular implicant, it must be that all the points in the onset are still covered. If they are not, then it is a wrong function. So, that check needs to be done in the process of identifying an implicant to be dropped. Yes, but an overall algorithm is not too complex. You can think of a lot of variations. The espresso is an example of an early logic optimization tool, where you are essentially doing the following: reduce, expand and irredundant in a loop until there is no further improvement. Why do you expect that loop to help? You perform reduction, you perform expansion, and in the process maybe an implicant got dropped, and we dropped some implicant. That irredundant step might result in what we called an irredundant cover. That is, you can't drop any more implicants from there and still manage to cover the function. Why do we expect a second iteration to result in a different solution? We will maybe understand in a little more detail as we look at how expansion is done, what is the issue involved there, and reduce and so on. But it turns out that you have a lot of choices. When you do expand, which of the available implicants, there is a set of implicants that you are trying to drop some of them. Now, what is the order in which you should process those implicants? That is one example. It is unclear. The quality of the solution depends on the order in which you do that processing. The other thing is, even after you choose the implicant to process, what direction should you expand in? Because there are n variables, you could possibly expand it in n different directions. That too we need to discuss a little bit, but what might happen is that in a future iteration you can try expansion along a different direction. That is why iterations are there in this process. The number of choices is large for each of these steps, for reduce, for expand and for irredundant also. But in the process we might actually end up hopefully escaping from some local minimum. Remember that irredundant was leading us to a local minimum, not guaranteed to be optimal, but this is an example of a possibly transformed version of what originally was given. Originally we started off with 5 implicants, but we dropped one of them, and this is an irredundant cover. Not necessarily optimal, we have already seen this. Yeah.
I was thinking that, so in the last, so we have number of directions to move in, right? There will be lot of iterations which we can do.
Yeah.
So if I plot the graph of improvements over each iteration, it need not to be an increasing or decreasing. So it can be a,
Yeah.
right?
Yeah, it could be.
So something like that. So it's more of like we need to look for global maxima.
I need to keep track of the best solutions so far. In each iteration we can explore different directions, but in the process we can keep track of what is the best result that we have got.
So we can keep, and we might have to come back then. So because if I just
Yeah, we would have to come back. We would ultimately of course come back and choose the one that gave us the best results, but this is a branching structure of the solution. You may need to come back to a previous iteration that looked more promising and explore that one further.
So can I map this problem to, so if we look at the standard algorithms of, for example, graph partitioning problem, so there the problem is more of finding a, so you keep on iterating and you find a maxima, you come back, okay, no, this was better.
But yeah, each of the levels may correspond to further improvement after having chosen an intermediate solution that looks promising. Initial iterations, maybe you choose some directions, all the directions are not necessarily promising, but you could evaluate the result of individual expansion along different directions, and maybe choose for further exploration those directions that seem more promising. And the standard search strategy is branch and bound and so on that are there, obviously apply to algorithms like this. By itself this loop is really not doing anything, it is just invoking those operations again and again. The intelligence lays in what direction you choose for each of those individual operations. Okay. So, it is possible that you have this kind of a solution that is kind of a local minimum, because you can't drop any implicants further from this. But if you apply reduce to this, maybe that implicant there is reduced to this implicant here is reduced to this. But this could lead to an expansion possibly in a different direction from what was tried earlier. Okay. Initially we had that being covered. Now we can have possibly this is an expansion, this is an expansion. So, I need to somehow keep track of what expansions I have done in the past, so that in future iterations I can traverse a different direction in the search space. But if I do this expansion, then you can see that there is one implicant there that could be dropped. On the application of the irredundant operation, I have a result that is better than what I started off with. That is the way in which reduce might make a difference. Again, by itself, that first step did not really change anything with respect to quality of the solution, but it enabled expand to occur in a different direction. That is what a typical loop of this algorithm might look like. Okay, this was a visual illustration. Its representation and implementation is also interesting. You have to be a little careful in implementing those operations, because they are invoked so many times. It is important that the implementation of those steps should be efficient. While this is not the only way to do it, this illustrates some of the issues that are involved. So, let us introduce this positional cube notation. I have a function like this. How do I represent it? We have talked about this off and on, we did not really get to the actual representation. This positional cube notation could use a binary encoding of a particular manner for the implicants. That encoding could look like this. If my variable is there in uncomplemented form, normal form like A, then I use a 0 1 to encode it. Why 2 bits? It is because I also want to take care of the do not care condition. So, if it was just 0 and 1, then 1 bit would have been enough, but I have a third thing to take care of, and which also leads to a fourth encoding that we have some interesting use for. But the presence of an A is captured by a 0 1, presence of an A prime would be captured by a 1 0. If both of these are 1, then it means it is a do not care, and if both of them are 0, then it means it is a void or a null. That has some interesting uses that we will see soon. But a function like this, a Boolean function like this, could be captured in this way, where you have one row for each cube. So, if there are 3 cubes here in the function, then you have 3 rows, and you have 2 bits for each variable. So, if A B would be represented as 0 1 for A, 0 1 for B, and 1 1 for C, meaning that C does not appear there. It do not care with respect to C, that particular cube is. A prime B C would be 1 0 because A is complemented, 0 1 because B is normal, and 0 1 because C is normal uncomplemented. So, that is what the representation would be for the Boolean function that we start off with. We can think of a few operations with that particular representation. Let us define an intersection of two implicants. Intersection would be defined as the largest cube that is contained in both of them. An example would be, let us say I have a cube ABC that is represented like this 0 1 0 all 0 1s. AB is represented like this, right. There is 1 1 here at the C position because C is not there. If I take the intersection of AB, C and AB, I should get what? AB, remember, is nothing but the sum of these two minterms, right. Those two. If C were the third variable that I have, that would be the 2. So, ABC, if you intersect, so anyway it is a function of 3 variables. So, AB corresponds to 2 vertices in that Boolean space. ABC corresponds to 1 vertex. The intersection of these two would be what? Would be this vertex, right, it would be that vertex. So, that is what the intersection essentially is, the set of vertices that are common between the two cubes. Right. This would be captured in our representation as follows. You look at the encoding for ABC, take the encoding for AB and you just do a bitwise product of all the 6 columns. What do you get? 0 1 is intersected with the 0 1, you get a 0 1, all the corresponding places are intersected, right. You take product of the here also you get 0 1, but the intersection of these two gives us 0 1, it is a bitwise product. So, I essentially have recovered ABC, which is the right intersection of those two implicants. Okay. What about this intersection? If I take ABC and intersect with A prime B C prime, what do I expect? Remember that space is like this, it is 3 dimensional and this is A direction, that is B direction and this is C direction, let us say this is 0 0 0. Then ABC corresponds to that point, A prime B C prime corresponds to maybe this point. What is the intersection of those two regions?
Null, void.
There is no intersection. These regions are not overlapping. Right? So, there is no intersection. That is captured in our operation here by the presence of a 0 0 in the intersection when you do that bitwise product. You take the product of 0 1 with 1 0, you get 0 0 and the existence of a single null literal anywhere there just tells us that this is void, there is nothing in that set. It represents a set of points and the 0 0 tells us that it is void, which is again a correct capture of what we expect in that intersection. Correspondingly, we can define a super cube of two implicants, that is the other way around. It is the smallest cube containing both the implicants, so union, but it is not merely the union, because you take again this example of this being one implicant and that being the other implicant. What is the smallest cube that contains both the implicants?
Both of them.
But it has to be a cube still. In fact, this is the smallest cube that includes both of those implicants. yeah, I need a single implicant. That is why we do not call it a union here, we are calling it a supercube, because it does include some other min terms that were not there in the original two cubes. That is why a different term is chosen as opposed to union, which of course has a connotation of the set of the min terms that are there in both of them. That is a different operation, but that is not the same as one region. That union of two cubes might result in multiple cubes. You might not get a clean single cube that defines the union. Sometimes you might, but sometimes you might not. If it were these 2 points, if you started off with that point and that point, then the union could be the same as the supercube, because you would get essentially a single cube that represents the union. But its computation should be easy. We just take the bitwise OR of the two implicants and I would get my supercube. So, between ABC and AB, if you take the bitwise OR, you essentially get zeros here 1 0 1. The third literal there would result in 1 1, because that is the union. This is 0 1 0 1 0 1 for ABC, and for AB I have the supercube would be the bitwise sum of these. So, which is 0 here, 1 here, 1 here, 1 1. What cube is this? This is AB itself. This is fine, right? If there is a containment relationship between the two cubes, one is a subset of the other, the supercube is just the larger cube. That is what you would get if you just do a bitwise OR operation. But like we saw, if you take ABC and A prime B C prime, which could be these two nodes, then you have a supercube where you had ABC was 0 1 0 1 0 1. So, A prime B C prime was 1 0 0 1 for B and 1 0 for C prime. The supercube would be the following: it would have 1 1 in both of these places. This place has a 0 1. So, the corresponding implicant here is just B, because this I would leave out and this I would leave out, and that really is this example that we have here. Right? This is an example where the supercube does have some min terms that were not there in the original two cubes. Okay, so that is intersection and supercube. Distance between two implicants is just defined as the number of positions in which they are different. Okay, so, the difference being computed like this. So, you have A B C and let us say A prime B C prime, then we will require the distance to be 2, because these two literals are different. On the other hand, if you had A B C and you have A B, then this distance is 0, this distance is 0. So, all three, this is a do not care, and that do not care anyway, there is an inclusive relationship. So, we will say that the distance here is 0. This is captured by performing an intersection of the two implicants and counting the number of voids. So, those are the operations. You can now see the reason why this notation was chosen in a way as to enable these operations, for example, because the intersection supercube, these operations are going to be performed again and again, we want them to be efficient. And if I can implement those operations as bitwise products or sums, you know that the actual translation into instructions and so on might be very efficient, and therefore, that is the basis of the choice of this encoding of implicants. Ultimately, it might translate to just a single instruction logical AND or a logical OR. If I manage to for example, capture the implicant within one word, if I manage to capture it within 32 bits of a processor, then this can actually translate nicely into just a single instruction. Okay. So, with that as the representation, how do I implement the expand operator? The idea is to increase the size of the implicants, so that later on other implicants are covered. The covering and actually deleting of the other implements that got covered is not part of the expand process, it is part of the redundant process. That also is not trivial, because you have to choose which subset of things that could be dropped would you actually drop, because you can't drop all of them. So, that is also a separate interesting problem, but expand itself is not necessarily trivial. Idea is trivial, but what are the choice? Problem is that choices are there. What are the choices? These maximally expanded implicants are the prime implicants. You can't expand anymore without intersecting the offset, means that you have arrived at a prime implicant. So, the expand process would result in a cover that is minimal with respect to single implicant containment. Single implicant containment means in the process of that expansion, you can make sure that that particular implicant that you are processing will not be covered at the end of that process. If you keep expanding, at the end you will come up with an implicant that cannot obviously be contained in any other implicant. That is the nature of the transformation, of course. When do you stop? You stop when you are intersecting the offset, which means that further expansion is not really possible. So, our basic operation then would be, in terms of that encoding, you raise one of the zeros to a 1 in the implicant. We want to drop one of the literals, right, either a or a prime if it exists, we want to drop. So, here this is what implicant is this? This is a, b prime, c prime. Right. Expanding it means that I convert this let us say to a c prime, means I am dropping the b prime literal. Conversely, I may drop a and that might become b prime c prime. Either way, this basic operation is one of those zeros is converted into a 1. Right. Dropping it means that a 1 0 or a 0 1 becomes 1 1. So, a 0 is converted into a 1 as the basic operation. Each such raise increases the size of the cube by a factor of 2. One literal is dropped means the size in that space has doubled. Right. I need to check if that expanded cube is still valid, which means that I check for a possible intersection with the offset. Yes. Assuming that this offset is available to me in the form of some set of implicants, I can quickly do an intersection of the expanded cube with all the cubes that are given, and together they contain the offset, or if the offset is given as a set of just all the minterms, that is fine. With each of them I can quickly do an intersection. Well, quickly is a little tricky, because the operation is quick with one minterm or with one cube. The number of such cubes might still be large. But the validity check is essentially an intersection operation with all of the minterms in the offset. So, that is the operation in terms of the implementation, what are the issues here? Issues are what order to consider the implicants. I have a large number of implicants, and the idea of course is to take an implicant and increase its size until it does not intersect anything in the offset. That is fine, that is easy to do, but the thing is, when I have a large number of implicants, then which one do I start with? That does influence the later steps and therefore the quality of my solution. Other thing is, having chosen that single implicant, what order do I raise those 0 entries to 1? That too is not obvious. You have a large number of variables, so all of them are candidates, and which ones to drop, which direction that expand should progress in, that itself is not obvious. Both of them are questions that are open, and we somehow have to use some heuristic to choose promising implicants and promising directions within those implicants. The heuristic could be that we expand those implicants first that are unlikely to be covered by others. Let us just quantify that with an example. Here is my set of implicants x, y, z and w, and that is the table for those implicants. The question is, which one is unlikely? So, which one should I start processing first, x, y, z or w? Here is one simple argument. You align them in that table and form a vector of the sum of each of those columns. There are 3 ones there, so that number is 3. There is a single one here, that number is 1. There are 3 ones here, which results in a 3. So, that is the sum. Now, you take the dot product of that sum with each of the individual implicants, okay, each cube, you get something. So, that is what we are saying is a weight. If you take the dot product of x with s, you get some number here 9. X is this. So, where did the 9 come from? Essentially 3, 3 and 3. Where it is 1, these numbers are picked up. Yeah, where this is 1, the corresponding number is picked up from the sum. So, you get 9 for x. So, the implicant itself, you take the dot product with the sum vector here, and you would get some weight here. That is what we are calling the weight. The operation clear? The dot product. What is the meaning of this? If the weight is low for one of those cubes, then it means that in the densely populated columns, that cube actually does not have a 1. Otherwise, it would have picked up the 3. Densely populated means if consider a column and there are large number of ones out there. If that cube also had a 1, then the larger number would have been picked up in the weight. If it is relatively small, it means that it has a 0 in the places that are densely populated, those columns that are densely populated. The argument is that if that number is low, if that weight is low, then because too many other cubes do not exist that have a 1 in that space, in that particular column, that cube is less likely to be covered by others. That is a heuristic argument, but if that number is high, it means that many others have a 1 there. So, it is more likely that it will be covered. Why is it 1 in that column? It is because our literal, if it is A, then either that cube has an A or it is actually do not care, right, both of which are favorable with respect to covering our implement. Right. If it is conflicting, if it is a 0, then it will not cover. So, the weight will be low if there are more zeros in that column relatively speaking. That is the intuition. So, less likely to be covered means that we can consider the implicants in increasing weight order. So, our first cubes to be processed could be the ones that have lower weight, because those cubes are likely to stay in the final result also, right. But the other ones, because there is a relatively larger overlap, those are candidates for dropping. So, since they are candidates for dropping, let us try to drop them, and instead let us try to expand the cubes that are less likely to be covered by others. So, that is why that order is what is resulting. Point is that we want to consider x last in this particular examples. X, y, y, z and w, it does not matter, the weight is the same, but x comes later. So, if I go ahead and expand an implicant, let us see what it looks like. So, originally the on set was these, there is a do not care set and there is an off set. I have one more point that I did not specify, it belongs somewhere. There should be 8 vertices, 8 minterms of course. Okay, actually the BC is okay, fine. These are actually cubes in the offset, so that is fine. All the 8 might actually be covered here. Since I picked up the y, say for expansion, let me expand y along the a direction, that would lead to the 0 1 becoming a 1 1. Correspondingly, that would lead to the new expanded implicant being y prime, where a is dropped, I have just b prime c prime. I have to check the validity of that new cube. This is the representation. I have to intersect it against all the cubes in the offset. And as it turns out, what happens if you intersect this with the offset BC? B prime conflicts with the B, so you have a null in the second position at least. Okay, actually this is B prime and this is BC. Right. So, that will lead to a null for the intersection with the first cube of the offset leads to a null. So, we are okay. Intersection with the second cube would lead to null in the third place, because there is a C here and there is a C prime here. So, I have here a cube B prime C prime that has a null intersection with everything in the offset. So, conclusion is it is safe to do that expansion. So, y prime is okay. Since it is okay, let us push further with respect to the expansion and try to drop something else. Now, let us try to drop b here. Right? If you drop b, then that 1 0 becomes 1 1 and I get the second expansion is just c prime. If you take c prime here, you will notice that that also leads to a null intersection with the offset, because it conflicts with both of those. They are in C form, and since I have a C prime, that is also a conflict, and therefore, this expansion is also safe, it is a valid expansion. After C, what is the next expansion? As long as it is valid, we will keep expanding. Right. Now, this one is valid. So, what is the next expansion? There is only 1 0 remaining, you try to get rid of that 0, change that 0 to a 1. What is the resulting function?
1 everywhere.
Yeah, it is 1 everywhere. It's yeah, everything is do not care. So, that one obviously has a non-null intersection with the offset. So, that is an invalid expansion. Okay. Similarly, I can take one of the others. If I try to expand W, then that would lead to something. So, that is my overall strategy. So, I have a table of these implicants and I know what the encoding is, what the representation is, my expansion would lead to one of those 0 bits becoming 1 and I do that intersection with the offset. In the process, it turns out that x and z are covered by that expanded y. Since I had a C prime here, C prime is what I ultimately pick up. So, I pick up two things, one is the second expansion of y, which I have indicated as y double prime. First expansion was B prime C prime, second expansion was C prime, that is what I would keep. Similarly, W is what I would also keep, that is my optimized set of cubes. In the process of that expansion, it turned out that x and z are already covered, I can drop them. You can see they are covered because you take an intersection of that with this, you actually get that term itself, that implicant itself. Intersection with y double prime will lead to, since this is do not care, whatever is there at A that will appear, and this one is not conflicting, therefore, whatever is there in that implicant will also appear. So, that is the expansion process and implementation would look like this. Second would be the order of raising the zeros in an implicant. The goal of course is to make that implicant prime, but just because there are many zeros in our implicant, it does not mean that we can raise all of those zeros to 1. So, some subset has to be chosen and the number of subsets of course is large. So, some heuristic is also needed here for choosing the order in which the zeros would be raised, because at some point you have to stop. You start with this, perhaps it is okay, the next one it is invalid and therefore you will have to stop. On the other hand, if you had chosen the third one to start with, you would have arrived at a different expanded cube. So, that order is essential. So, let me keep a set free of the candidate entries that can be raised. Initially in this example there would be 3, this just refers to the position number 2, 3 and 5. All of this are an initial free set, okay. But they are candidates, that does not mean that all of them can be raised, we have to check the validity to see which ones can be raised. Anyway, it is initialized to those 0 entries. In the process of raising, we would drop some elements from that set. Of course, if you manage to raise all the zeros to 1s, then that set is empty. Some pruning of the search space can also be done here to reduce the number of choices that we have. For example, first we can find entries that can never be raised. What entries can never be raised? Suppose my offset was this, consisting of 1 cube, and this is the cube under consideration that we are trying to expand. This cube has a distance of 1 with the offset, right. It is different in the third position. So, the distance is 1. Remember, if there is a do not care somewhere, then that does not count towards the distance. Right. So, there is when there is a conflict A versus A prime, that is when there is a distance. You are counting the distance as the number of voids that are there in the intersection. This is essentially one void. If the distance is 1 from the offset, then you can't raise it, because that would lead to a non-null intersection with the offset. It is different at this point, right. It essentially is different because of that entry, and if that entry is raised to a 1, currently it is a null intersection, but it will lead to a non-null intersection. That is not allowed as part of the expansion process. So, if those implicants are at a distance of 1, then those corresponding entries because of which that distance is 1 are ones that we can throw out, we need not consider those entries. Similarly, you could argue that there are some entries that can always be raised. Let's see an example of this. That is my cube under consideration, and this is my offset, and we are considering that position, this 0. This column has only zeros in the offset. Okay. Since it is only zeros, here too I have a 0 1. There is no harm in raising this to a 1. It will not lead to any further intersection with the offset. There already is some intersection. Whatever is there, if there is a distance, it came about because of some other position, not because of this position. So, it should be okay for me to raise this to a 1, since all the other elements are 0 there. All the elements in the offset are 0 there. Then I can say that it is okay to raise it. So, I can raise and remove them from the free list. These are somewhat trivial sort of cases, but otherwise what we are looking at is, if the supercube of x and y, remember it is obtained by taking the bitwise OR of the two cubes, if it is feasible, feasible means that there is no intersection with the offset. So, where x is the implicant that we are considering, y is one of the other implicants that we have with us. If it turns out that it is feasible for some y, you raise the corresponding entries in x. This is okay, right? As long as we are not intersecting the offset, it is okay to raise it in whatever direction. Specifically, it is okay to raise it in a direction where a supercube is formed with one of the other implicants. Why is the supercube relevant here? So, I had some terms, these are the offset terms. Okay. Let us say this is one cube and this is some other cube. The supercube of those two cubes, it turns out, is in this space. That is, this is the supercube. It is there in a space that does not intersect with anything in the offset. So, we are saying that we will prefer to expand along a direction that results in that supercube. Why would we prefer that?
So, logic would become smaller the larger the cube that we are taking.
Right, the logic does become smaller. Remember, our ultimate objective is to not merely reduce the size of them, but the number of implicants that I am covering. Choosing the supercube leads to what possibility? This was my x, this was my y. The point of choosing the supercube is that I could drop that other guy. I am considering x. This is the implicant that is under consideration. We want to see what directions to expand it in. It could be expanded in different directions, but the profitable direction of expansion is one in which I am able to ultimately drop one of the other implicants. Supercube is a nice thing that helps us here, because if I choose the supercube, it means that one of these become redundant, the both of those become redundant, but one of course is the result of the bigger one is the result, the supercube is the result of expanding one of them, but in the process I would have dropped one of the others. I may have a choice of expanding in some other direction which might have led to some other logic that is less profitable, because it does not result in that containment relationship that we want to move towards. So, that is the operation, and among the different choices that we might have, x is the one under consideration here, and the supercube with y could be taken, supercube with z could be taken. It is possible that when you take the supercube with z, In fact, maybe it intersects with one of the others, therefore, it is not a valid supercube, right. So, you would select that y that covers in the process the maximum number of other cubes. It's also possible that not only is y covered, as a result y is covered in an obvious way when you expand x into the supercube of x and y, but it's also possible that in this process there is some other cube that gets covered in that supercube. Remember, supercube consists of not merely the union of two, but some other min terms also possibly. That's really some essential ways if I want to distill the logic. These are the things to take care of in determining the order in which the zeros can be raised in an implicant. So, two questions need to be answered for expansion. One is the order in which the implicants are going to be processed, and other is for the implicant that is being processed, the order in which the zeros would be raised to 1. Moving on to the reduce operator, idea is now to convert a prime implicant into a non-prime implicant. The whole point of reduction is that it is no longer a prime implicant, right. It violates the definition of a prime implicant. However, the number of implicants in the cover still remains unchanged. In fact, even because of expansion, the number is not changing. It is just that redundancies are created in the process of expansion. We will drop them as part of a different operation perhaps. So, the number is not changing, and a validity check needs to be made, just like in the expansion case I made the validity check that we are not intersecting the offset. Here the validity check is the other way around. We have to ensure that as a result of the reduction, what condition still holds. The onset points are all still covered as a result of the reduction. Right. So, I want to find a maximally reduced cube. Here too I need some heuristics, but let us define this maximally reduced cube first. So, I have some cubes, let me represent this as a set. So, I have my x, that is one cube, and I may have some other implicant. So, this is a cube y and maybe some other cube. These are my f. That is my function. First of all, let me generate f minus x, which consists of essentially the remaining implicants, the remaining cubes, if you just remove that cube from there. Here is what I can do. F minus x is it consists of this much, right, that and this together. So, that is my f minus x. I take the complement of f minus x. Complement with respect to set means what? What is the complement in this picture of f minus x? Each is seen as a set. X is a set, y is a set, z is a set, and actually formally complement is defined in terms of a universal set, everything other than that. What is complement of f minus x?
1 minus y minus z.
So, if you just remove the y and z, all these others form the complement. That is my complement. So, f minus x prime is this. So, what we are saying is that reduced cube that we want is the intersection of x with f minus x complement, which gives us what?
The center part.
Yeah, this part of x that is not overlapping with the others. This is clear that that would be the maximally reduced cube. I can't reduce it any further because then I would drop some things from the function, but these parts of x that are overlapping with y and z, I can afford to drop from my reduced cube because they are already included in y and z anyway. So, that is all that we are saying. X intersection f minus x prime is what is my reduced cube. Okay. This is fine as the definition, but the problem is that f minus x prime, that reduced cube, this is just a set of minterms, right, that might not result in one cube, it might actually become multiple cubes. That you can see that if you have, let us say these were my original x and that part was covered by y, this part got covered by z, then my maximally reduced cube consists of this, but this is not one cube, this is actually a set of minterms. So, I can't possibly have that whole thing. The problem is we want to replace x by exactly one cube, that is part of the reduce operation. In the process of doing the reduction, we should not increase the number of cubes that are there. That is through all of these operations we try to make sure that we are moving in a direction of reduced number of cubes. So, we do not want to increase the number of cubes. What happened is we all had individual cubes that were all nicely structured, but the complement operation interfered with the single cube property. It resulted in a possible multiple number of cubes. Intersection is fine actually. If you take the intersection of two cubes according to our definition of intersection, you get only one cube, that you can see in the representation itself, right, there is only one cube that is there. But then since the complement resulted in a disjointed set of minterms that do not necessarily form a cube, the intersection of x with that complement also may result in multiple cubes. Then the reduced cube that I am interested in is the supercube of f minus x, x intersection the supercube of f minus x prime. That is the reduced cube that we are looking for. Just because f minus x prime is no longer possibly just one cube, it may be more than one cube. That this is actually the maximally reduced that we will leave the proof of, but you can see that it must be safe to do it. There is a larger cube is formed of that complemented set, and anyway we are intersecting that with x, means that we are choosing only from what was there in x. So, it must be safe to do that. So, that is the idea. So, this is what theoretically we are looking for as the reduced cube. Let us try to do it quickly on an example and its associated representation. Suppose I start with this function in which I have two cubes, one is b prime, which is the square, and the other is a prime c. Its representation is this. So, for x this is b prime and for y it is a prime c. So, that is my initial function. I would like to reduce something. Let us try to reduce x. What is f minus x in this example? F consists of, what is f here? It is the set of all the cubes that we start off with. So, x and y, that is the set of all the cubes. So, f equals just x and y. What is f minus x? Just y. You remove that element, what remains, that is f minus x. What is the prime of f minus x? Prime is defined in terms of the universal set. All the minterms that are not there in y, that is the prime. So, you see that this may lead to multiple cubes, because y was this, right? This is my y. So, the set of all minterms that exclude y's is essentially the set of these 6, all of these 6 minterms, that is f minus x prime. In fact, that results in 2 cubes here, you can see one is this square that would cover those 4 and the other is this square. This is where the number of cubes is increasing in that complement operation. Okay. Then what is the supercube of those 6 terms? It is essentially of these 2 cubes. From the representation you can see supercube of those 2 cubes is obtained by taking the bitwise OR, which is essentially the entire space, everything. So, that is the supercube. Now, when you take the x intersection supercube of f minus x, that is my definition of the maximally reduced x that I can afford. So, that when you take that intersection of x with everything do not care, you get x back, which means that x cannot be reduced further. X has to be there, you can't reduce x further. That should be clear in the following way. X is the square, right? If you reduce it, what happens? If you choose along this direction to either pick up these 2 or those 2, that would be a reduced cube. Both of them would be illegal, because in the process we would be dropping some minterms from the onset. Or it does not matter even if you pick up these 2 or these 2, because all 4 are there in the onset, you can't really afford to reduce it in any direction. Okay. What about reducing y? It seems that there is a possibility for us to do something about it, but formally we have to take f minus y prime. What is f minus y?
X.
F minus y is just x, because f consists of just x and y. So, that is x. So, x prime for us, since x is the set of those 4 points, x prime is the set of those other 4 points. Now, this actually has a reasonable overlap with this. When you take the intersection of y with this set, now you do get something. So, supercube of f minus y prime is what? F minus y prime is the set of those 4 minterms. Supercube of those 4 minterms, each taken as a cube, is what? You end up with 1 cube only, right. This is an example where the supercube results in just 1 cube. So, that is what it is, and y intersection with this is just a reduced version of the y. You can see that this part of y is overlapping with x, you need not have it in the reduced form. That part definitely needs to be there, because there is no other prime implicant that is covering it, but that actually comes out here in our computation of y intersection f minus y prime. So, the result is that y could be reduced for us to a smaller region in a way that between x and y we are still covering all the elements in the onset and we are not leaving anything out. These are a little further insight into couple of those operations. I have omitted irredundant. There are 3 operations like expand and reduce and irredundant, that I have omitted, but the set of operations and the kind of things that you do is again similar.